Okay, so according to my clock, we're ready to start. So welcome to our makeup lecture. I guess just for everyone on the webcast, this is maybe 25% of the class here, something like that. So not everyone could show up, and we knew that would be the case. So it's imperative that this screencast work today. So this is our makeup lecture. We will have lecture tomorrow and during our regular times as well. So we will meet again tomorrow at 12:30 in 213 Wheeler, just in case someone was thinking differently. You have a homework assignment due tomorrow at 5 p.m. I guess that's all I really need to talk about in terms of logistics. Any other logistics I should talk about? I guess your labs have started too this week, and I saw some emails from Yang around sending around a SPICE model file for you to use for your lab number 1. You got your lab number 1 last week, so I think logistically everything is going smoothly, right? Yes.
Are we supposed to go into lab?
Yeah.
Okay.
You should go to lab, because what's going to happen is your TAs will talk about background for that. He'll talk about the model file and that sort. So definitely go to lab this week. Okay? All right. So I'm just going to jump right into lecture then and just remind you what we were talking about last time, which is these MOS inspection formulas. And so we talked about inspection formulas for bipolar, and last time was all about MOS. And the main difference between bipolar and MOS, just to jog your memory, is that in MOS, the beta is infinity, right? And so that makes the input resistance, which is R pi, also infinity, because R pi equals beta over GM. Maybe I'll even write these down here. This is in your notes from last time, but beta goes to infinity for MOS, and that means that R pi, which equals beta over GM, that also goes to infinity. Okay, so these expressions that you see down here, which you also got last time, are exactly the same expressions that you had on your inspection formula sheet, which is this sheet right here, this section of it, which was for bipolar, except now we've just massaged them into MOS-type equations by just letting R pi go to infinity, by letting beta go to infinity. But the last thing that we did was say that that wasn't quite enough. Right? So you have beta going to infinity, R pi going to infinity, but finally you also have to have GM go to GM plus this GMB, where that GMB is a transconductance that's particular to an MOS device that the bipolar device does not have. And this has to do with the body of the MOS device. So a bipolar device is a 3-terminal device, and MOS device is a 4-terminal device. The 4th terminal is the body, and so we have to account for its GM in certain cases. And what are those certain cases? When do we have to account for that GM, the GMB? You remember?
When there's a body source bias?
Exactly. So when, in cases where we tie the source to the body, you don't have to worry about GMB. And that's what we covered in the last lecture to a great extent. But for cases where the source is like this, so it's tied to ground or tied to anything not the bulk is tied to ground or tied to anything that's not the source, then you have to take into account this GMB. Okay? And so these formulas that you have here apply for when the substrate is grounded, the substrate being the bulk, or when the well is grounded. So I could even say substrate or well, okay, is grounded or tied to VDD, which would be the case for a PMOS device. Okay? All right, so we did a actual small signal analysis for a small circuit last time to prove that this GMB comes into play, but I'm going to do one more just so that you're a little more comfortable with this. And so let's just do a little example that further expresses the effect of this GMB constant that's coming into play here. So this is just one more example in addition to the example that you had last time. So this example will make it very simple. I'm just going to take this MOS device right here. I'm going to tie its gate to ground. and I'm going to tie its bulk to ground, as is happening on this side here. And I'm just going to take the simplest case where I ground out the drain of this device. And then from the bottom, I want to measure the input resistance seen looking from the bottom. So this is the resistance seen looking into the source. That's what we've been calling RS, right? So what is that RS? And you have the equation for RS on the left side here, but I'm just going to derive it for you right now, just to give you a little more comfort with the fact that GMB has to be there. And so the way that we derive these resistances is we drive the terminal that we're looking into with a voltage source, a test voltage source, which I'm calling Vx, and then measure that current that goes in there. Okay? And if you have this equation memorized, you have no problems. You could just write down what that equation is. But instead of memorizing now, let's just derive this here. And this is how you would derive any of these things, using small signal analysis. So here's the equivalent circuit for this transistor. Right, so it's the hybrid pi model. Across this I have my VGS voltage, where this is the gate. That's the source. You know that you have a current-controlled current source here. Sorry, voltage-controlled current source. That's GM times VGS. But you know that for MOS, because the body is not tied to the source, you also have another voltage-controlled current source here that has the value GMB times VBS. And then finally you have the R0 resistance, which like last time I'm just going to call by a conductance, which I'll call GDS. So GDS again equals 1 over R0, where you're used to using the R0, but in this case I'm just going to use the conductance there. Okay? Yes?
Shouldn't that actually be like 1 over GDS because it's a resistor?
No, but see, I'm using all of these. Actually, for conductances, you also give the same symbol.
Oh, okay.
So right, it depends on context here. Okay. And so it is GDS, and I could call it either GDS or R, and you would have to know the context to know whether it's 1 over. Okay. Okay. And what else here? So I have, in addition, right, I'm driving this bottom thing with this Vx test source. So there's my Vx test voltage, and I want to measure this current going into that. So Vx is plus and minus around that. Okay, and then finally, where's my bulk terminal? Where my bulk terminal I'll draw out here. We've grounded that bulk terminal, so that's B. This is D up here, the drain terminal. But the bulk terminal has a voltage across it of plus to minus here, and that's my VBS voltage. Okay? And so with this, I can pretty quickly write down some expressions here for example, VGS. So VGS, I could see just by looking at the polarities with Vx right here, that's going to be equal to minus Vx. Okay? And also looking at the polarities with VBS, that's got the opposite polarity of Vx as well. So I could say all this is also equal to VBS. Okay? And if I look at VD right here, VDS, right, this is just going from this node to ground. So that voltage, if I had to write an expression for VDS, that's just going to be minus Vx. So all of these are the same voltage. All of them are minus Vx. And I can very quickly write out an expression for what this represents. So basically, since I have only Vx across each of these current sources, right, so this current source becomes GM times minus Vx. This current source becomes GMB times minus Vx. All of this stuff up here is really just equivalent to a single resistor that's going to ground that I'm driving from the bottom and looking up this way. So here's my Vx, and there's my Ix pushing into that. This is the resistance I'm looking at here, and this resistance, or conductance, I can call GM plus GMB plus GDS, okay, which means that the total resistance that I'm looking in, this RS that I'm looking for, that RS is then just going to be 1 over all of these GMs added together. So GM plus GMB plus GDS. And, you know, I can even write this, if you want this in terms of resistance, I can write this as 1 over GM parallel with 1 over GMB parallel with R0. Okay, and since R naught is so much bigger than these 1 over GM parameters, you can finally write this as RS is about equal to just 1 over GM parallel with 1 over GMB, which you can also write as 1 over GM plus GMB. Okay, and so this really verifies the equation that I have written right down here, that if you look up into the source terminal of this transistor, you see 1 over GM plus GMB. Okay, so all I did was derive this explicitly for you using the hybrid pi model. You can also use a T model, get exactly the same result. You should have plenty of experience doing this kind of derivation from your 105 class. Maybe even from 40 you did some of this. Not sure. Some of you may have done this in 40. But I've derived this for you, and the point is, like we've been doing for most of this class, once you derive it, just remember it. Don't derive it again. You're going to see this case again and again. Don't rederive it. Just remember that this is the answer looking up into this source. And if you can remember just these simple equations here, then you can do your circuit design much faster. Okay, and again, you don't even have to memorize these equations here. You really only have to memorize those inspection formulas that are associated with the bipolar devices, because you memorize these equations here, then you let beta go to infinity, you let R pi go to infinity, you replace GM with GM plus GMB, and that gives you the MOS formulas. Okay? So it may seem like I'm asking you to memorize even more expressions, but I'm not. Just get the bipolar ones and adapt them to the MOS ones. Okay? And so there's still just 6 equations here, really, that you need to commit to memory. And a lot of them look the same, like these gain things here, except for a plus or minus on them. Okay, so it's not difficult to memorize this, and I encourage you to do that. All right, so that's what we've been talking about, again, is midband analysis. What we really want to get to now is frequency response. So frequency response is also something you looked at in your 105 class, but I want to teach you how to do it faster if you don't already know how to do that. And some of you may already know how to do it, but some of you have not. Again, it depends on who you had for 105. Okay, so let's talk about how we can do frequency analysis now by what I'm calling inspection. And let me add a new slide to that. Okay, so let's talk about a new topic now, which is frequency response. And the first thing I want to talk about when I mention frequency response is, what does the frequency response for a typical amplifier look like? And the concept of a dominant pole. All right, so let's talk about this concept of a dominant pole. So again, we're talking about amplifiers, and so maybe the amplifier that you know so well right now is this op amp. So if I take this op amp like this, and I drive this op amp with some input, and I sense the output of this op amp here, then I can plot a Bode plot for the response of this op amp. And I guess I'll just make clear that inside this op amp, inside the op amp is actually a network of transistors. So it's going to look something like this at the very input, like this. Okay, so you have this inside the op amp. And we're going to talk about exactly how that's implemented later in the course. But this is why I care about op amps, because it contains your transistors. And the nature of those transistors, the way that they're hooked up, is going to dictate what the transfer function of this op amp looks like. And so let's draw a sample transfer function for this op amp. So we're basically going to draw a Bode plot for this, which will jog your memory a bit about Bode plots. And so on this axis, I'm going to plot the gain of this amplifier as a function of frequency, so of j omega, right, which is equal to V naught over Vi of j omega. Okay, and I'm going to plot that, since it's a Bode plot, in dB values. Okay, and so this is going to look as follows. It's going to have some region here where the gain is flat, And then you know from previous courses that what starts happening is it starts rolling off. As soon as you hit a pole, you start getting a roll off here. And how fast does that generally roll off? Does anyone know the slope?
20 decibels per decade.
That's right. So 20 dB per decade. Let me make that a little less steep so I can draw this a little better. So the slope of this thing here is going to be at 20 dB per decade. But that might not be the only pole that it has. Right? That's its first pole there. But usually any of these circuits, if they use more than one transistor, is going to have many poles. And every time you have a pole at whatever pole frequency it has, it's going to increase the rate that this curve changes by another 20 dB per decade. Okay, so say I had a second pole right here. So this is the first pole right there. I can call that omega P1. That's my first pole. But say I had a second pole right here, omega P2. If that's the case, then what's going to happen is this thing is going to start decreasing at a faster rate here, which is 40 dB per decade. I'm just adding 20 dB per decade to this original decrease rate that this had. Okay, and it can keep going beyond this. So I could have yet another pole here, which could be my omega P3, and then that would start decreasing at an even faster rate due to this other pole. All right? So just simple Bode plot formulations there. The other interesting thing that I want to cover right here is the phase between these poles. So do you guys remember how to write out the phase for this? So this is a log omega scale that I have. This is still a log omega scale. And on this scale above, I plotted the amplitude. But now let's get the phase. So let's get this phase of A of j omega. Okay, so what about that phase? How would you plot out the phase of a transfer function that looks like this? Okay, first thing you want to do is project down where all these poles are located, because those poles, like they shape the transfer function for this circuit, will also shape the magnitude transfer function, will also shape the phase transfer function for this circuit. And so what do you remember about how you do the phase for this? Do you remember any certain rules from your Bode plot days, which is maybe EE40 or 105? Did you do Bode plots in 105? Yeah, you did. Yeah.
A decade before a pole, you start going down at 45
Excellent.
degrees per decade.
Yeah, that's right. So what you do is you look for the decade. So a decade before. So say this point here corresponds to omega P1 divided by 10. And this point here corresponds to 10 times omega P1. If that's the case, then I can draw asymptotes that define how the phase is going to change. And so after one pole, so say there's only one pole in this circuit right here, where will the phase end up after one pole?
90 degrees different.
Exactly, 90 degrees. So the phase starts out at 0 degrees here, but then it's going to end up at this 90 degree level. And I'm also going to draw on here in preparation for the next pole a 180 degree. And I can keep going here, which I will for completeness, 270 degrees there. Okay, so you sort of plot out these asymptotes. And so what these omega p divided by 10 and omega p times 10 do is they kind of tell you where those asymptotes should go. So I can draw something like this and like this, and I can draw a line from that point to that point, and that becomes the asymptote for my phase, which I'll draw in blue here. So my phase curve now looks like this. Comes out like that. It goes through that asymptote like that, and then curves out like this. Okay, so that helps me to draw the phase for that particular pole. That's how the phase changes as the frequency goes through that particular pole. Okay, and I can do the same thing with the rest of these poles. And so, for example, for this pole, I can go 10 times down, 10 times up. So this is omega P2 divided by 10, 10 times omega P2, project these down, draw the asymptote that these correspond to right there, and then I sort of have to mesh these two phases together. So now this phase actually is going to drop down a little faster to go through that asymptote, and we'll do this. Okay, and so on and so forth. For this next one, the phase is going to do something like that as we go through that next pole there. So that's what the phase response ends up looking like. And so what you're noticing is that phase changes quite a bit after you go through these poles. And we're going to get to this much later in the class, but we're going to be very concerned about what this amplitude plot looks like and what this phase plot looks like in relation to the amplitude plot, because that's going to affect stability. And so remember, we're talking about an op-amp here. So we're talking about this device here. When we put this in negative feedback, we want to have a stable circuit. But if you put it in negative feedback, and because of these phase shifts, you actually end up with positive feedback, which is what happens if you're operating at a point where the amplifier is 180 degrees phase shift. You're not going to have a stable circuit. It's going to go unstable. Okay, I'm saying a mouthful right now, so if you don't understand what I'm saying right now, then don't worry about it, because we're going to spend 2 weeks on this towards the end of class. Okay, but stability is a big criterion. I guess the main thing that I want to talk about now is that this distance right here, that distance between the first pole, omega P1 and omega P2, that decides how stable a negative feedback circuit will be. Okay, so let me just write that down. So the distance between omega P1 and omega P2 must be large, I'll say in general, for a stable op-amp feedback circuit, op-amp negative feedback circuit. Okay, so what does that tell us? That tells us that we can define omega P1 as a dominant pole. Okay, because that means omega P1 is going to be much less than omega P2 for stability. And anytime a pole is much less than any other pole in the system, we will identify it as a dominant pole. Okay, so omega P1 becomes what we'll call the dominant pole. All right, so this is all just preliminary to our frequency response discussion. So I want to make sure that you have an understanding of this right out from the start, that in most of the problems that you will look at, there will be a dominant pole. And it turns out that just that fact alone makes it possible for you to start doing inspection analysis for frequency response. Okay, because our method for doing inspection analysis depends on the fact that we have a dominant pole. Okay, once we don't have a dominant pole, you're going to have to change the method for frequency analysis, and we will talk about that later on as well. Okay, but for now, let's assume we have a dominant pole. Okay, so that in hand, let's now move on to what I have as some prepared notes, because I don't want to write all this stuff down in real time. But this is stuff that you should have seen in a previous course to some extent. It may not have been called what I'm about to call it here, but at least the method, you should have seen this before. And that is how to determine the first pole, or the corner frequency, of an amplifier's frequency response. Okay, so just to start out here, you can recall that the transfer function of any amplifier, it could be an op-amp, or it could be any of the amplifiers that we're talking about based on transistor circuits. It can be expressed as a function of frequency by way of this transfer function. So A of S, which is the same as this, right? I could have called this also A of S, where S equals j omega, right? S is just the complex frequency variable, is equal to some midband gain. And that's what we've been deriving up to this point. Okay, we've been doing midband gain calculations. That's the gain that you get if you look at this plot here, which is also a Bode plot. It's a more complete Bode plot than this one. Right, this Bode plot to the left is basically showing everything from this point on. but it's not showing what really happens when you get really close to zero frequency, to very low frequencies. Okay, and remember, there's no zero frequency on this because that's log omega. Right? This just keeps going to 0.00001, but it never goes to 0 because it's log omega. Okay? And so I can write the whole transfer function as A sub m, midband gain, times f sub L of S, which is sort of a frequency shaping transfer function. That when you multiply it by the midband gain, gives you this roll-off as you go to lower and lower frequencies. So this is going to happen a lot of times because of the way that you bias your amplifier. Okay, so off-chip circuits will usually have this kind of roll-off. On-chip circuits a lot of times don't have this kind of roll-off, but we'll talk about this anyway, just because you should know how to calculate this frequency. By far the more important frequency is this one up here. And so to model this frequency response, we're going to multiply the midband gain, which you get using the inspection analysis you've just done in the previous lectures and in your homeworks, by now a transfer function f sub h of s that stands for the high frequency transfer function that shapes the way that this curve looks. Okay, so all we're doing now is trying to figure out for different transistor circuits, and I'm about to go into several examples, what this shape looks like, at least for the first pole for now. And later on in lecture, we'll get the second and third pole, and we'll figure out how to get those poles. That takes a little more work than what we're about to do. So the way that you get this first pole, okay, is using a technique called open circuit time constant analysis. And I don't know that you learned it by that name. Did you learn it by that name? No. Was it called anything when you did it? Zero value time constant analysis or anything? No, it was never called anything? Okay. I'm going to call it open circuit time constant analysis, and you'll see why. Because the way that you do this is you open circuit all the capacitors that are going to cause this frequency response. Okay? But first, just a little bit of background on why it is that this works. And I'm not going to be able to do justice to this in the lecture. This is actually detailed quite a bit in Gray and Meyer. So that's one of the nice things about the Gray and Meyer text. They actually go through this analysis. A lot of the other texts do not do this. They don't go through this kind of analysis. And so you're sort of left in the dark as to why this works. You're given a procedure, but you don't know why. Gray and Meyer actually teaches you why this works. They go through a whole determinant derivation. I recommend you look at that derivation because it's insightful. The reality is you don't need to know that derivation. If you just know the procedure, you're okay. All right? But I'm going to talk a little bit about this. So in general, this f sub h of s, which again is this transfer function that models just this part of the curve, this f sub h of s, let's put this up there, in general is a polynomial, right, where it has a numerator with a lot of zeros and a denominator, of course, with a lot of poles. But for this f sub h, the number of poles is greater than the number of zeros. So that stands for number of poles. And this stands for number of zeros. Okay? And so in general, you can always make up a polynomial like this. From your 20N class, I'm assuming you learned how to take a polynomial and factor it into all of its poles and zeros. Is that correct? You had to have. Yeah. So you know that you could take any polynomial like this and you can always turn it into this, where this pi stands for multiplying each of these factors, and you have all these factors of 1 minus s over 0, 1 minus s over a pole location there. In general, you can always do this. Now, usually, if I assume that all the zeros and poles are on the left half plane of the complex plane, which makes it a stable circuit, which I think you learned in 20N as well, okay, then I can say that this is also equal to 1 plus s over omega pi, the numerator terms, and the denominator terms 1 plus s over omega zj. All right, now I could also say that if I have all these factors here based on these poles and zeros, if I focus just on the poles, which is all that's important for me right now, later on we'll address those zeros, but much later in the class, because they will have an effect actually. But for now, just looking at the poles, this B1 coefficient in this f sub h just through math, I can tell that it's going to be equal to the sum of all these pole locations, omega pi's here. Okay? So just through the math of all this, that's the way that this works out. Okay? And that means I could call each of these 1 over omega pi's. Now that's 1 over frequency. 1 over frequency is the same as time, right? And so 1 over frequency is the same as a time constant. So I can call this tau pk. That's a time constant. And so now you see where the time constant in this comes in. Right? We're basically open circuiting capacitors, and then we're calculating time constants based on the circuit that you end up with the open circuited capacitors. That's why I call it this. Now, continuing with this thing, through network theory, and this is where Gray and Meyer does all this math that I'm going to not talk about here. Okay? You can get from this point here, okay, where these things are not necessarily related to this B1 here, right? But you can prove that the sum of all of these time constants from 1 to n sub p, where again n sub p is the total number of poles you have, is going to be equal to the sum of all the capacitors and this Rj naught, which is a driving point impedance, multiplied together. Okay, so each of these makes a time constant, and you're adding all these time constants together to get this time constant here. Okay, that's not an obvious thing yet. So you have to read through Gray and Meyer if you want to see the full explanation for this, and they do a great job explaining this, I think. Okay, but I just don't have time to do it here. Yes?
So if fh of s is the frequency, like the shaping function, then why is it that the magnitude goes down when you like get close to a pole? Because wouldn't that mean that it would be like going up, like or like a
Well, what happens is when you get to a pole, so look at this right here. So if s gets larger than omega pi, then suddenly this term becomes greater than 1. And it's a term in a numerator that's getting larger,
okay.
and so the whole thing gets smaller.
Yeah.
Yeah, so the math does work out for that. Okay. And so if we go back to this here, the definitions for these things are right here. So C sub j are capacitors in the high-frequency circuit, which is basically your small signal circuit that you know how to make, by zeroing out all the DC sources, voltage sources, opening circuit all the DC current sources, right? The same small signal circuit you've made before, that's which capacitors these are, the CJs. Okay, they're the small ones. Okay, Rj naught is the driving point resistance seen between the terminals of CJ, okay, which I'm going to have to define for you. So it's a driving point resistance. I'm going to define that for you by doing an example. Okay, but it's driving point resistance seen between the terminals with all small capacitors open circuited. Okay, so small capacitors means on the order of 1 nanofarad or less. Okay, that's a small capacitor. If you have a capacitor like that, you open circuit that in this calculation. If you have a capacitor that's large, like greater than a microfarad or say greater than 1 nanofarad, that should be short circuited in this analysis. And then finally, all independent sources, you short the voltage sources, you open the current sources. So you're zeroing out those independent sources, okay, which is the same thing you've been doing for the midband analysis. All right, so what you're going to end up doing is calculating a time constant like this. And you're going to calculate a time constant like this for every capacitor in the circuit. So that's with the J. This is J from from 1 to however number of capacitors are in the circuit. You're going to add all those together, and what you're going to really be getting an approximation to is the dominant pole. So there's where it's required that you have a dominant pole. Because if we can assume that we have a dominant pole, then you have an omega p1, you have an omega p2, and all the way up to omega p np, where again that np stands for number of poles. Right? That's the total number of poles. But if omega p1 is much less than all of those other poles, then from this equation right here, for b1, I can neglect all of these. Right? Because if they're much larger than omega p1, they're going to contribute such small terms compared to omega p1 that they just don't matter. Okay, so what I'm going to do is after I calculate all of these time constants and add them up, I've actually calculated all of this. Okay, but I'm going to neglect all of these and say that that's equal to omega P1, and that's going to give me my omega P1 as long as omega P1 is the dominant pole. Okay, if it's not the dominant pole, this doesn't really work. Okay, but I will tell you that even if it's not the dominant pole, we still do this, right? And we still do it even though it's not supposed to work because, again, we don't care. We don't care that much, right? For frequency analysis, if you can get within 2 times of what that frequency is, you're good. You've done a great job hand analysis, right? So what you're learning to do is hand analysis to quickly get frequency response. And then what you will do is plug into something like SPICE, which will do a lot better job of determining exactly what that frequency is. That's the way you should do circuit design. And so I'll say this many times during this semester, but there's a lot of circuit designers out there. And the worst circuit designer is the one who will build a circuit, plug it into SPICE immediately, and never write anything down. Okay, circuit design is more intuition. It's more your understanding of how to do this. Right? Your understanding of if I change this capacitor value or if I move this transistor to this configuration, that's going to affect the frequency response this way. Okay? That you can get very quickly by just writing down a few equations. But if you do it all by SPICE or some kind of simulation program, you'll have no intuition. You'll be changing something and you don't know why you're changing it. Okay? So it's much better to have the intuition, and that's what this analysis is for. It is not exact. Okay? It will not get you exactly that frequency corner, but it'll get you pretty much close to where it is, which will allow you to make a decision as to whether this circuit change was good or not. Okay? And so, again, we're making approximations, and we're very happy to do it. Okay? That's the attitude you need to have. Now, there is one thing I can say. When there is no dominant pole, you can still use an approximate expression like this. Okay, where you can say that omega h is equal to 1 over the square of this omega P1 plus 1 over the square omega P2 minus these zeros, and that will get you to a much closer estimation of what omega, the cutoff frequency is for this, omega h. Okay, but let's not go into detail. This is just FYI. We're not going to worry about this because when we start looking at dominant poles versus not dominant poles, we're going to do the analysis completely different. We're going to have to look at the circuit, figure out what nodes contribute to dominant poles, which ones contribute to non-dominant poles, and that's going to take at least half the course for you to get a comfort level, to be able to look at a circuit and figure out where the poles will be. Okay? But right now, having given you this, let's go ahead and apply this technique here to an actual example, because there's nothing better than an example to show exactly how this should be done. What do I do here? Okay, so let's take the simplest example that we can take, and that's the example of a common emitter circuit. So, example, high frequency analysis of a common emitter circuit. So I'm calling common emitter just CE. Okay, so usually you'll have a circuit that's biased up, just like the one we looked at as the very first circuit we analyzed for midband analysis. I'm not going to draw all that stuff. I'm just going to go straight in and sort of draw its small signal circuit here, which is this. So I have some load resistance R sub C that's loading my transistor, which in this case is bipolar. We'll do some bipolar examples and some MOS examples later on. And this has an output. I have some bias resistors here that were R1 and R2, but I'm just going to call it RB here. And let me move this a little toward the right to give myself more space. And then I have a source resistance called R sub S. And finally my source V sub S. Okay, so I want to solve this circuit here, but what I want is its frequency response. I want to know where that cutoff frequency is. I basically want to find omega h. So find the cutoff frequency or often called the 3 dB frequency, which I will call omega h. Now, let me make that continuous. Okay, so what's the first step that we need to do? So the first thing I want to do is identify the capacitors that I'm going to have to worry about in this circuit. Okay, so where are my capacitors? Well, this comes back to the small signal circuits that you were playing around with in the first few lectures that your TAs were giving you. Okay, so I know that I've got a capacitor right here. That's C pi associated with that transistor. I know I've got another capacitor right here from the base to collector, that is C mu. And then finally I've got one more capacitor that I should worry about for bipolar, and that is this collector to substrate capacitor, CCS. Okay, so I've identified the important capacitors in this circuit. And so now what I have to do, and these are the capacitors CJ. Okay, so these are the CJ capacitors that we're talking about on this side of the screen. And so now I have to handle each capacitor CJ one at a time and determine the time constant associated with that capacitor. So let's go ahead and do that. So let's find tau 1. Okay, what do I mean by tau 1? Well, I'm going to label the nodes. So I'm going to label that 1, and I'm going to label this node 2. Okay? And so whenever I label nodes, I put a circle around it. But usually when I put a circle around something, I mean I want everything in shunt with that node. And so how do we do this analysis? Well, you want to have inspection equations for this analysis too. But it turns out for this particular analysis, I don't even have to have an inspection equation. So I'm not even going to refer to that inspection sheet. On that inspection sheet, I do have some equations down here that are for high frequency analysis. Okay, maybe we'll look at this just for a second here. So here's your omega h, right? That's going to be equal to 1 over all of these time constants. If this is a generalized transistor like the generalized transistor above it for the midband analysis. But if you look at this, I've got a tau associated with node B. That means a tau associated with all the capacitance in shunt with B, which I'm calling C of B circled. Okay? And then there's likewise for a C circle and E circle, I have taus associated with those. Okay? That's associated with any capacitance in shunt with that node. So when I have a little circle around it, that means in shunt. Okay? But for capacitors that are not in shunt, like C mu, right? That's not in shunt with that node. That's connecting two terminals. So it's not in shunt. I also have time constants associated with C mu and with C pi. Okay, if they're not going straight to ground. Sometimes they are going straight to ground, and we'll show that. But if they're not going straight to ground, then there's a couple more equations you have to memorize here. Okay, so that brings your total number of memorized equations to 8 now. And don't worry, this is the last few that you have to memorize. And you don't even have to memorize one of these if you remember the Miller effect. Okay, but right now, so for r pi naught here, for r pi naught, there's an equation for the driving point resistance across C pi that you can derive using just your analysis with the hybrid pi circuit, the small signal analysis with hybrid pi. Another equation here for r mu naught that is associated with C mu. Okay, really the one you have to memorize is pretty much just this one here, this r pi naught. If you memorize that one, you'll be good because this one comes readily from the Miller effect. And you don't have to memorize the Miller effect. Well, I guess you have to have that in your head, but that's very easy to memorize. Okay, so with that, let's do an example here. So let's find tau 1. So what do we mean by finding tau 1? I'm going to go ahead and, to be very explicit, just redraw this circuit here. So there's your RC. There's your Q1. And I have two resistors coming out in this direction. So I have an RB here and RS. So again, using this methodology here, all small, less than 1 nanofarad capacitors are open circuited. And so I have open circuited CCS. I have open circuited C-pi. Whoops, I don't want to, I'm trying to do tau 1 right here. And C-pi is the only capacitance I see in shunt with tau 1. Okay, well actually I do open circuit them all. Okay, so I open circuit all of these small capacitors. But then at this point where C-pi used to be, or at my node 1, which is what this is, I'm going to put a voltage source here, Vx, and measure that Ix there. And from that voltage source, I'm going to determine the driving point resistance. Okay, so the driving point resistance at that point, which I'll call R1, that's the driving point resistance in shunt with that, is going to be equal to Vx over Ix. Okay? And you notice that voltage source is taking up the position where C-pi used to be. Okay, so let me just write that. Takes up the C-pi position. Okay, the additional thing that happened in going from that circuit to that circuit is that C-pi, C-mu, and CCS all got open circuited. Okay? Because they are the small, less than 1 nanofarad capacitors. Let me write that down too. Less than 1 nanofarad caps. Okay? So I've converted that to this circuit here. And now I could go ahead and push a voltage and measure currents or so, but I know what this driving point resistance is right at this point. And so do you. You could do that just by inspection. So can someone tell me what that is? What is that resistance seen right at that node?
R pi in parallel with RS parallel RB.
Exactly. So R pi parallel RS parallel with RB. Okay, that's my driving point resistance. And so if that's my driving point resistance, now I can write down an expression for that first time constant, tau 1. That's just going to be equal to the capacitance that I replaced with this voltage source Vx, which was C-pi. That was all the capacitance going to ground. You notice C-pi is not just going from the base to the emitter here. It's going from the base really to ground, because the emitter is grounding. Okay, so that's the capacitance in shunt with node 1. Okay, so I could say that C1 equals C-pi, which is C1 in your inspection formula thing is C-pi. So now I can call this C-pi times R pi parallel with RS parallel with RB. Okay, that's my first time constant right there. Any questions at this point about what I've done? So I'm following this procedure here, but I'm doing it very explicitly here, but maybe I'm not being explicit enough. Sometimes I'm not, because I just run through. Are there any questions about this procedure? Yes?
What if the emitter is not tied to ground?
Yeah, if the emitter is not tied to ground, that'll be the second example that I do, but just for now, that would be this case, right? And so now you could not just use the shunt resistance for the driving point resistance. You would have to use this equation. Okay? So because it was tied to ground, it made it much easier for us. We did not have to use this equation. Okay, but if it's not tied to ground, you would have to use that equation. Okay? And speaking of not tied to ground, let's do the next one now. Okay, so let's find the time constant due to C mu. Okay? And so I'm going to call that T mu naught. Because C mu, right, it's not associated with any node. It's not associated with node 1 or node 2. So I can't say that it's just the capacitance associated with that node, and then I can't use a driving point resistance that's just associated with that node. I actually have to go in and solve the following circuit. So here's the RC. Here's my transistor going to ground. I still have my RB and my RS resistors. I open circuit all of the different capacitors, but I replace the capacitor that I'm interested in, which is the C mu, because I'm getting the time constant due to C mu, with a voltage source. So now I have to replace C mu with this. I have a Vx that I'm driving this, and I have to measure its Ix, and I have to calculate this R mu naught equal to Vx over Ix. Okay? And so to calculate this, I actually have to go into the small signal circuit. I have to write out the hybrid pi model and solve this thing. Okay? But I'm not going to do that because that's already one of your inspection formulas. I imagine you did this in one of your previous classes, like 105 or so, right, to get the driving point resistance for this. From the inspection formula, there it is. That's the driving point resistance. Okay, so it's equal to RB, RB circle here, which is the resistance you see at the input, shunt with the input. Okay, plus RC circle, which is all the resistance in shunt with this node at the collector, plus the GM of this, and notice it should be the capital GM, okay, which in our case is equal to little gm because we have no emitter resistor, times the resistance in shunt with the collector times the resistance in shunt with the base. Okay, so that's the expression that we need to use to calculate this R mu. I'm going to write it in terms of our nodes here. So this then is equal to all the resistance in shunt with node 1, that's R1 circle, plus all the resistance in shunt with node 2, that's R2 circle, plus GM times R1 circle times R2 circle. Okay, and that's just an equation that you're going to have to memorize if you want to do it this way. Okay? So you have to memorize the equations for the things that are not in shunt with the nodes. All right, so if I go ahead and apply this equation, then I can write my R mu naught directly here. That's just going to be, first of all, R1. What's this R1 circle? Can someone tell me?
RS.
Excellent. So it's RS parallel RB, but there's one more.
R pi.
Yeah, parallel with R pi. Remember, it's in shunt with that node there. And then what's this R2? All the resistance in shunt with that node. Yeah, it's RC, but to be complete, I'll do R naught in parallel with RC. But you're right, you can neglect the R naught in most cases. And then, finally, this last term is just GM times both of these terms we just wrote down. So GM times RS parallel RB parallel R pi times R naught parallel RC. Okay? And so we have that driving point resistance, and so we can now write that T mu naught is equal to R mu naught times C mu. So there is our second time constant that we're going to need to determine the frequency response of this whole thing. Okay? Any questions about what I just did here? Any questions at all? There are no stupid questions. Yes?
I see the formula sheet says the GM is a capital GM, not the small GM.
Yeah, that's right. And so I guess I skipped a few steps here, but see, this is capital GM here, right? Because capital GM is usually equal to GM over 1 plus GM times RE, right? But RE in this case is 0. And so because RE equals 0, GM just equals little gm. Okay? So that's what I did there. Let me be clear about a couple things. Let me also write this, that this circle here means in shunt. Just want to make sure I've written down a lot of the things that I said. Okay? And so let's now find the last time constant that we have here. We've covered C pi. We've covered C mu. Now the last capacitor we have to cover is CCS. And actually I should think of it as node. The last node we have to cover is node 2, for which the total capacitance at node 2 is CCS. Okay, so let's go through here and let's now hit node 2. So find the time constant at node 2. And so we're just really going to be able to write this out now. So the time constant at node 2 is equal to whatever the driving point resistance is at that node. And the driving point resistance at that node is just all the resistance in shunt with that node, which we can write down fairly quickly.
RC.
Yeah, it's RC to be very explicit, I could say R naught in parallel with RC. I don't know why I'm doing that today, just because I haven't told you what RC is. It could be like a mega ohm or so, in which case I have to take into account R naught. But usually you'll neglect the R naught. So the tau just becomes this R naught parallel with RC and times the CCS. Okay? And so that now is our third time constant. And now I can just write as a solution for this that the total, that the cutoff frequency, the high frequency cutoff for this, if we have a dominant pole, is just the sum of all of these time constants, which we have equations for, and 1 over that. So that now becomes my high frequency cutoff. If I were to plot for this amplifier, its Bode plot, I will have this, and that would be omega h right there. Okay, that's what I've determined. Okay, so pretty simple the way that this goes through. You're just following procedure over and over again. But in this, we actually had to use a memorized equation. Okay, what if you just don't want to memorize that equation? Well, you can still do it even without memorizing that equation. And so this is something that I think you've seen before, and that is to use Miller's theorem. Right? So you all should know about Miller's theorem here. And this just makes the determination of this frequency response a lot easier if you just remember Miller's rule, which is, well, let me first draw the circuit again here. So there's my RC, there's my transistor, there's my output voltage, this is Q1. I'm leaving a lot more space so I can draw things in. So there's RB, VS, and RS. Okay, so that was our original circuit. Now we want to solve this using the Miller's theorem. And to do that, let me switch to a different color here. Let's use red for this. So all the capacitors I need to care about, I'm definitely going to need to care about this capacitor here, which is C pi. Okay, I'm definitely still going to need to care about CCS. But for C pi and CCS, I didn't have to memorize any formulas. Right? To get the driving point resistance, I just had to get the resistance at these nodes. Right? This was node 1, that was node 2. As long as I can get the resistance at those nodes, which is easy to do because it's all resistors in parallel, I don't have to memorize any equations. The device, or the capacitor I had to memorize equations for was this one. Right? That was C mu. Okay, so that's a problem capacitor for me. So what I want to do is get that capacitor out of the feedback path. The reason why it gives us problems is because it's in the feedback path. Right? And so like I said, anytime you have something in the feedback path, it's going to force you to do more work. You have to do small signal analysis, that sort of thing. Now, we did the small signal analysis. Well, you did it in some previous course. And we're just memorizing the equation. Or you can say, I don't want to memorize that equation. I know C mu is there, but let me not treat it as C mu. Let's get rid of it. Okay, and let's turn it into two capacitors. So one capacitor in shunt with the input, and one capacitor in shunt with the output. Okay, and the values of these capacitors are determined by Miller's theorem. So this capacitor now becomes equal to C mu times 1 minus whatever the gain is, A sub V. So that's the gain across Q1. To be explicit, from base to collector. Okay? Whatever that gain is, I'm going to take 1 minus that gain, and that's the new value for that capacitor. Okay, what is the gain across this? So I can write out this capacitor. Yeah, it's just GM times RC, but it's minus GM times RC, because it's a common emitter. So that minus turns that into a plus. So that's what my gain becomes there. So the new capacitor that I stick right here becomes C mu times 1 plus GM times RC. Okay, just from Miller's theorem, which I suspect you've learned in 105, correct?
Yeah.
Yes. Okay, then at the output you have C mu times 1 minus 1 over A sub V. Okay, since A sub V is very large, right, this just ends up being C mu. Okay? And so now I have two new capacitors to deal with, but the whole problem becomes a lot easier for me. I can just say, now I can just get all the driving point resistance at node 1 and 2. Now I don't have to worry about this C mu going across a feedback path. So now I can just write directly that tau 1 is equal to all the resistance I see in shunt with that node, which we got before. That's just R pi parallel with RS parallel RB. But now times all the capacitance in shunt with that node, which is now C pi plus this Miller capacitance, C mu times 1 plus GM times that RC. And so that's now my new tau, but it's a total tau at node 1. Okay, and now I can do the same thing for node 2. And so at node 2, I just get all of that resistance in shunt with that node, which is just RC. Really R naught parallel with RC, but now I'm going to do the, I'll do the whole thing. Okay? And then times all the capacitance in shunt with that node, which is now C mu plus C sub S. And then finally, from both of these things, omega H is just 1 over the sum of these two time constants. So the important thing is to account for all the capacitors in the circuit. Okay, and we accounted for all the capacitors in the circuit. There's no T mu in this case, but T1 and T2 you could see includes the T mu. So if you compare the two solutions, right, this was the driving point resistance for the C mu capacitance. It multiplied RS times RB times R pi times C mu. You could see RS times RB, parallel, RS parallel RB parallel R pi. So R pi parallel RS parallel RB, that's multiplied by this C mu, because the 1 times C mu. Okay? That's also multiplied by GM times C mu, which you see right here. GM times that C mu times that, but also times the output resistance, which you also see right there. Okay, so the two give identical solutions. If you want to split it up into the Miller, into a Miller type problem, that's fine, because that's easier to remember. Okay, so it really comes down to the only thing you really need to remember is this equation right here. Okay, this one you can take by the Miller effect, but this equation, that one you got to kind of commit to memory. Okay, so let's now do an example where that one becomes important to account for. So this is a multi-stage example. Okay, so for the multi-stage example, let's go back to that emitter-coupled pair that we had looked at before. So just this circuit here. Okay, so here's a circuit we had played with before. And again, as before, Q1 and Q2 are identical. And so what we want to do is find our high-frequency cutoff omega H. And so now, as before, we have to account for all the individual capacitors that are important in this circuit. And so let's draw in, write in some of these capacitors. So the first capacitor is going to be a, let's make some room first. Is capacitors associated with Q1. So I'm going to have a C pi 1, and I'm going to have a C mu 1 connecting base to collector. And finally, I'm going to have my CCS, my collector to substrate capacitance. And I'll have the same kinds of capacitors for Q2. So I'll have a C pi, that's a C pi 2, a C mu 2, and I forgot to show my output node, so let me do that. And then finally I have a CCS2. Okay? And I want to solve this in exactly the same way. So I'm really just showing you procedure after procedure on different circuits. And so I'm going to identify my nodes. So that's node 1. We call this node 2. And this output node I'll call node 3. And so I want to handle each capacitor one at a time. And so node 1, this is a simple node here. Well, first of all, I can do some simplifications out of this whole thing. And what are some of the simplifications I have? Well, first of all, I look at this CCS1. Okay, in the small signal circuit for this circuit, or for this emitter coupled pair, you had the bias thing earlier on. I showed that in the previous lecture. But in this small signal circuit, this is grounded here. And so you've got ground at both ends of CCS1. That means it's simply not there. Okay, we're just going to neglect it because it's got both ends grounded. It can't do anything in this circuit. Okay? And that simplifies a couple things because that also identifies to us that this C mu 1, right, whereas in the previous problem it was a problem for us because it was in a feedback path. Now it's not, right, because C mu 1 is going to ground. So it's now shunt with that node. And so I can now say that tau 1, which is all that time constant at that node 1, is just going to be equal to the total resistance in shunt with that node times the total capacitance, which I know is just C mu 1. Okay, so what's the total resistance in shunt with this node here? We've done this before. You remember?
RS parallel REE parallel 1 over GM2.
Not quite. Yeah.
Or RS, no, never mind.
So you do have an RS going that way. That's correct. The RS is correct. And it's parallel now with any resistance you see looking this way.
Yeah.
Okay, so what's the resistance you see looking that way?
R pi 1 plus, multiply 1 plus RE parallel to 1 over GM.
Okay, so if I look this way, I'll just do it up here. So that's right. So that's R pi 1 plus,
1 plus beta
okay,
multiplied by RE parallel to, the RE parallel to the other, that one
1
that
over
you see over
GM2.
there.
that's 1 over GM2. And so if RE is much bigger than 1 over GM2, which it generally is, it's this. So that's R pi 1 plus R pi 2.
2 up.
Yeah, so that was a 2R pi there. So we derived that in the previous lecture. So I'm just going to put that right down here. That's the driving point resistance associated with capacitor C mu 1 now. And so that's it. That's my first time constant right there. Okay? Because C mu was tied to ground, it made it a much simpler problem for us. And that's nice. All right, so let's try the next capacitor in line here. So I could see that I have a C pi 1 here. Okay? So with that C pi 1, what's the driving point resistance across that C pi 1? It's going to have a time constant associated, which I'll call tau pi 1. So I'm going to have to take C pi 1 times something there. Okay, so that's not as easy because, again, that's not going to ground. It's not a capacitor going to ground. It's a capacitor going from one terminal to another terminal there. Right? And so what I want to be able to do here is just write down that expression, and that's where you got to kind of memorize this expression right here. Okay, so unfortunately, this is one that has to be memorized. Okay, so I got an R pi in parallel with RB plus RE. So RB represents not the shunt resistance at this node, right? This is R capital B. So in this nomenclature, R capital B means all the resistance seen looking that way. Not in shunt with that node, but looking out of that node. Okay? And RE likewise, everything looking out that way, and then divided by 1 plus GMRE. Okay, so if you have that as your formula there, then, right, I can just write that in. So this is going to be an R pi 1 right there, parallel with all the resistance I see looking out this way here. Okay, all the resistance I see looking out that way, that's just RS. Okay, so I have RS there, plus all the resistance I see looking out in that direction, which is technically REE parallel with 1 over GM2, but I'm just going to neglect the REE because that's going to be generally a very large resistor if it's used in biasing. So I'll just say this is times 1 over GM2 there, and then all of this divided by 1 plus GM1 times 1 over GM2. Okay, so that's what I would have to calculate to get this driving point resistance for tau pi 1. But see, it's not so bad. If you have that expression memorized, you can just write it down. Okay, if you don't have that expression memorized, then you're going to have to draw out the hybrid pi model. You're going to have to do a bunch of things to get that time constant. Now, there's one thing I do want to tell you, though, is that oftentimes this is a neglectable capacitor. Okay, can anyone tell me why it is that I'm saying that's a capacitor you probably can neglect oftentimes? Not all the time, and in fact in this problem you can't neglect it. Okay, but why would I be saying that, gee, if you see a problem where the C pi is necessary, so say I had something like this. Let's do an aside right here. It's an RE. Say I had something like that. Let's really make an aside by, whoops. Oh, I can't really make it aside. I want to change the color, but I'm not going to be able to. But anyway, why is it that I would say that C pi can be neglected in this situation here a lot of the times? So here's something to consider. A capacitor is not really there if it has no voltage change across it. Okay? And so this circuit is actually the circuit for a follower, right? Which means if I have some voltage here on this node, right, this is going to have about the same voltage, right? These two are going to be about equal, which means that I'm not really having any variation across this capacitor, right? So if that's the case, then you probably can neglect the time constant due to C pi. Okay, so if gain V naught over Vi equals 1, then you can often neglect the tau pi naught. Okay, the time constant due to C pi. Okay, so why is it that I'm saying in this circuit that you probably don't want to neglect that? Remember what the gain is from here to here? The gain from here to here is about 1/2, not 1, right? Because of this loading by 1 over GM2. So if you remember that 1 over GM2 makes that voltage divider that gives you a gain of 1/2. So that's why you do not want to neglect this C pi in this case. And the other thing is C pi is usually a lot bigger than C mu. Right? It's usually about 10 times, at least 10 times, maybe 20 times bigger than C mu. Okay, and so you got to be careful. Even though the gain is about 1, right, sometimes a C pi can have significant effects if C mu is extremely small. Okay, so you do need to be careful, but I'm just telling you here that oftentimes that C pi can be neglected. And so, for example, you're running out of time on an exam, You just say neglect C pi, and more than 50% of the time you'll be okay. Okay? Just some practical stuff for you. All right, so we handled C pi, which I think is probably the most difficult capacitor to handle in this whole thing, because the rest of this just follows through pretty easily here. So now I've got this node 2 that I have to care about, and so I want tau at node 2. And so what's that going to be? What's the capacitor associated with node 2? Anyone tell me? So look at the circuit here. It's node 2. I already accounted for C pi, so I don't need to include that in node 2 anymore. Exactly. So there's C pi 2, but what's C pi 2 doing? Is it a difficult capacitor like what we had?
No, it's going to ground.
Yeah, it's going straight to ground right there. Right. This gate is grounded here, so C pi 2 shows up there, and now it's got to be multiplied by the driving point resistance in shunt with node 2. What is that resistance? Someone tell me?
GM2?
Yes, 1 over GM2 is definitely there.
Parallel.
I was going to write a different one first, but
Yeah,
me
1
write
over
that.
GM2 parallel.
okay, 1 over GM2 parallel,
RE.
REE,
And 1 over
which I
GM1.
could neglect, but I won't here.
Yeah, parallel 1 over GM1.
Okay, except you're making the same mistake I made during the time we looked at this.
Plus
1 over GM1,
plus RS over beta plus 1.
RS over 1.
exactly, plus RS
Over
over
plus
beta
1.
plus 1. Excellent, good. You guys are really picking this up. Okay, so very simply, there it is. That's the time constant for that. I can neglect REE usually because REE is usually very large. Okay, so I'll say REE. That's where I'm neglecting that. Okay, so now I've got just one more of these to do. Right, I've handled all the capacitors except for one now. Right, and so that's this C mu 2, actually two of them. I have C mu 2 and CCS2. They're both tied to this node 3. Right, so they're both going to contribute a time constant that I can call time constant at node 3. And C mu 2 plus CCS2 times whatever the driving point resistance is at that node, which is simply RC2. Okay, it's RC2 times a 2R0 as well if you want to be complete about it, but we can neglect that 2R0. And so now omega h, I can write the whole formula. Just add up all the time constants that I have here. Tau 1, tau pi 1, tau 2, plus tau 3, and 1 over that. That then becomes my corner frequency for this amplifier. Okay? So we've done several different amplifiers, but all of them are bipolar versions. Let's now tackle an MOS version here. Now, what about MOS? So in MOS, we actually have to use the inspection formulas again, and I'm going to explicitly choose an MOS amplifier, two-stage amplifier here, where you have to worry about some of those feedback capacitor cases. Okay, so here it comes. So this is a drain resistor RD1 going into MOS device M1. And I'm going to ground M1. So that's basically a common source type configuration. I'll go into this with a voltage source that's driving a resistance RS. And this then is going to drive another stage that is loaded with a resistance RS2. And I'm going to take my output right here. And this is a common drain type configuration, which is just like a common collector type configuration. This is M2. Okay? So, nothing really different here. Really the same kind of analysis, except possibly even easier, because we're just going to go around neglecting our pi's and that sort of thing because they're infinity, right? The betas become infinity too. So it's the really the same thing that we were doing with MOS before. All of the betas are infinity, all the R pi's are infinity. You have different capacitors though. Not really different. There's only so many capacitors you can draw around a transistor, and here they are, right? Instead of C pi, this becomes CGS1. Okay, this becomes CGD1. And I even have a shunt capacitor out here, which I'm just going to call CDB1. Okay, and for this second transistor here, same kinds of things. I'm going to have a CGD2. I'll have a CGS2. And if you look at that CGS2, you may say, okay, that thing may cause a little bit of trouble there for you. I guess to be complete in MOS, if I'm going to do CDB1, which is the drain to bulk, I should also have a CSB1. And same thing for this device here. I'll have a CSB2. And finally, I'll have a CDB2. Okay, so those are all my capacitors there. It seems like a lot of capacitors, seems like a lot of things to take care of, but first thing you should do anytime you see any of these problems is try to simplify it as much as you can. So where can I do some simplification in this? Simplification means eliminate. Right? I can eliminate that capacitor because it's going from ground to ground. I can eliminate this capacitor also going from ground to ground. Okay, so I've eliminated those. And now I can start doing my whole analysis, but we're out of time, so we'll do this analysis tomorrow at 12:30 in our regular room. Okay? Thanks for coming, guys.